Well, hello, this is Steve Cline, and this is case study review number 2 for remote sensing of rivers. Um, this case study is based on some research done by Oki and Yasuoka from 2008, titled Mapping the Potential Annual Nitrogen Load in the River Basins of Japan with Remotely Sensed Imagery. This was of interest to me because it seemed like kind of an opportunity to look at some of the things that we've been doing in class. Specifically, one thing we've been doing this week and expand it beyond just the river system itself and look at applications for, like in this case, pollution estimations, which could be used in a place like Japan for planning of land use. And so I came across this just by accident. Happened to be the same week that we were doing some land cover classification. So thought it was very interesting and timely. Just a quick background note on why this is applicable in a place like Japan. If you look at the shape of Japan, it sits, and where it sits in the world, it's on the Pacific Ring of Fire. In fact, a few days ago there was a fairly large earthquake in Japan. I believe it was the southern part of the country. But the result of that is that it's a long, narrow country with mountain ranges running down the kind of the spine of the country. Very mountainous, which means river channels are fast moving. They're mountainous, and they're relatively short by comparison to rivers in North America or South America or anywhere else pretty much in the world. These are fairly short river systems. Also, Japan is a very densely populated country, so there are not large stretches of pristine wilderness on these river systems. And so it was a good opportunity, it looked like in the study, to look at a lot of different types of land cover. And specifically, this study was looking at discharge of not so much phosphorus, but nitrates and ammonium from several of the major river systems in the country. And because of the topography of Japan, the fact that these are a lot of the results are non-point sources, and the pollutants come from fairly large areas. It makes it difficult to determine the source of pollutants. So that was kind of the challenge of this. The researchers note that models that are aimed at assessing the effects of land cover on eutrophication, which just means, I believe, human-made pollution, they've focused mainly on small-scale areas and on agricultural lands. This study was aimed at looking at a way to build a model that could be using all different types of land cover and could be exported perhaps to even the global scale. And specifically, they were measuring nitrogen loads in the rivers, and they were looking at nitrates and ammonium. And the data that they got was readily available data from the Japanese Ministry of Land and Infrastructure and Transport. Quite an acronym, I'm guessing, for that one. So the question they're asking, is it possible to predict nitrogen loads in river systems based on the land cover of that system? So the study area that they worked on were 30 different watersheds. The data sets that they had included 299 individual watersheds throughout the country, and they selected 30. And these 30 were based on the variation and the fact that they represented a cross-section of the river systems throughout Japan. So they had data for the dependent variable on every river system, but they selected these 30 because the explanatory variables were easier to come by, and they created what they felt was more of a representative sample of the river systems. The first thing they start with is they create a land cover classification, and they used something that we just used this week, which is the NDVI, very simple algorithm. And they used what they called a 12 monthly maximum NDVI data set. So they took the day of every month where they got the maximum amount of good pixels from 1996. And they used, just like we did, the near infrared and the red bands. These were low resolution data sets. They were 1.1 square kilometers in resolution. So this is something that's going to be a countrywide type of an assessment tool or a continent-wide assessment tool. And they note that the advantages of this coarser resolution data is that the data sets, they were more widely available, which allowed for the removal of cloud cover, and they could also take into account seasonal changes in the data. From this classification system, they created 5 classes, and you can see them in the legend of the map, ranging from urban area to all the way through natural vegetation and agricultural land as well. How do they determine the relationship? Well, they used and tried to improve upon a model that apparently has been around for a while, which they called it the conventional model, and you can see it goes back to work done as early as 1967, and it's based on the relationship between the nitrogen load and the river flow in a particular river basin. So that formula at the top, what those variables stand for is the Li over Ai is load per area. So they're looking at load of nitrogen in kilograms per year. And so there's a formula, of course, to determine that based on the measurements that they get at the mouth of each river system. And then area is just, square kilometers for that particular I river system. K is a coefficient that they've developed, as well as N and M. Q is annual river flow in the river basin. S is the total nitrogen load accumulating in the river basin, and you can see the formula below how that is determined using the 5 different classification systems. And then area is, of course, just area. So in the formula below, they're using a couple different variables, which U is let's see, U is the kilograms per square kilometer in a year within a given river system, and area, that area prime Ij is land cover for each area, each river system, in each land cover category. So there's land cover and river system variables in that one. And then the coefficients along the bottom, they were determined using the simplex algorithm of estimation, looking for minimums and maximums in order to come up with the best variables for the equation. And then they took the 2 data sets, one for all the river systems in Japan and one for land cover, and they were able to extract land cover per the 30 sample sites that they were studying. And so the first thing they did was they evaluated the formulas. Do they work? They took nitrogen concentrations that were measured in milligrams per liter at the mouth of each river, and they determined load by multiplying the nitrogen concentration times 10 to the negative third times the quantity of water flowing from there, and they got the load. And so what they did was they took the test formula and they estimated the load using the test formula, including the coefficients that they had come up with. And then they actually measured the annual load and compared the two. And they actually compared it for 2 years. So they took the 1996 data in order to determine if the coefficients were reliable with seasonal changes. They compared 2 different years of actual data to the estimations that they came up with based on just the land cover data. And they found that the association was very strong. This chart is actually the 1997 data. So the comparison between the estimates and the actual measurements for the 30 sites had an R-squared value of 0.96. So very strong association between the estimate and the actual measured nitrogen load. So then moving on from the 30 test rivers, they extended this to all of Japan to produce a map of total annual nitrogen, or sorry, potential annual total nitrogen load based on these land cover data sets that they then had. And they found that, I mean, this makes common sense, but urban areas tend to have the highest potential total nitrogen load out of all the river systems. And they figured that the reason why this was the case was because in urban areas there was more runoff resulting from air pollution. So those pollutants in the air are going into the river systems when it rains over those urban areas and over those river basins, those watersheds that have a lot of urban land cover within them. And so then they were able to extend this study to look at the effect of these larger areas and try to measure pollution over these large areas. And they found that the higher nitrogen values of load values were in urban areas as compared to all others, and that the forested areas had the lowest impact on nitrogen loads. And they figured that the index maps that they create are useful for risk assessment of pollution on lakes and in the ocean, and can be used as potential aids in assessing environmental risks. So, for example, if there's a development proposal under review, these maps could be used at least within the specific river system to estimate potential risk of the development on nitrogen loads at the mouth of the river. So water spilling into the sea or water filling up in the lakes, is this development going to be environmentally hazardous for those environments? And so again, interesting to be able to take something that we were using in class and see it, being applied in it's still river systems, but it's it's about as far away from what we're doing in class in the middle of Wyoming as we can get to apply it to a countrywide analysis like this. And I found it interesting, and hopefully you did too.